I am Alexandra Balahur, and I am the team leader of SEMIC, the Semantic Interoperability team in DG Digit. And I am here with different members of my team. We are happy that you joined us for this presentation. So the agenda of the talk today, we will first have a brief introduction about the SEMIC context and what we do in SEMIC in terms of semantic specifications. Then we'll talk about MLDCAT-AP and the DCAT-AP ecosystem. We will have a guest talk from OpenML. They were all actually the reason why we have also started working on the MLDCAT-AP, so the collaboration that brought about the idea of developing an application profile for machine learning catalogs or portals. And then we will have a closer look at the application profile for machine learning models. And finally, we will conclude and speak about the next steps that we would like to take. So yeah, perhaps before we start, there are some practicalities because we are in this webinar setting. Please mute your audio if you are not speaking. Please ask your questions through the chat, and just know that the workshop will be recorded. So if you do not want to appear in the recording, just turn off your camera, and then that should be fine. So without further ado, we can start diving into the context of the SEMIC assets. As you may know, SEMIC is the Semantic Interoperability community. It already has quite a bit of history in the past more than a decade, building different assets, semantic assets, with the mission to promote semantic interoperability among the EU member states. Apart from promoting interoperability, we actually deliver pragmatic support by building different specifications, by updating them, by engaging with the community in order to see what are the next steps in these specifications as well. And we help with technical implementation if challenges arise. At the core of our community are the semantic specifications that we build. They are open and free to reuse data models, and you might be aware of the CoreVox, DCAT-AP, CPSV-AP, and the different extensions of these core specifications. We also develop pilots, and in this sense, we look at new technologies such as AI, and linked data in order to further provide specific solutions for public administrations in their efforts to scale up their interoperability maturity. Additionally, we have a very strong knowledge hub. And in this knowledge hub, we have different tools that are available, tools that help to build, to implement the specifications, but also tools to edit and validate these specifications, and learning materials for the different technologies, but also for the different tools that are implemented in SEMIC. Moving further, more specifically, these three different lines of activities are expressed through focus areas, 5 focus areas. The first focus area is the semantic specifications, including extensions, and that also we have seen is extremely useful in the context of data spaces, where we have developed different extensions for DCAT-AP. Specifically tailored for the domain of specific data spaces. Additionally, we are working on the catalog of services specification and implementation of different catalogs of services. We are working on base registries, specification of base registry application profiles, but also the interconnection of base registries. We are supporting in the interoperability policy implementation. And finally, we have a new line of work, which is on AI for interoperability for AI, which means how can AI support with building interoperability tools, and also how interoperability can support in the quality of and trustworthiness of AI. Moving forward, more in focus of specifications. How do SEMIC specifications enable interoperability? Well, they make data transparent and available. They support the coherent implementation of laws and policies. They help implement cost efficiencies, and they help digitalization and the harmonizing process. This, of course, applies to interoperability as such. So building on the principle of interoperability, what we do with our specification is enable semantic coherence across different implementations of assets. We have two categories of specifications. So the core vocabularies, which are sort of the basic brick a cornerstone element of semantic interoperability, and they're like the core units to building a standardized approach for describing key concepts. And in SEMIC, we have different core vocabularies, such as the one describing persons, businesses, organizations, and locations. Additionally, application profiles, they build on the core vocabularies, and then they add a set of use cases to define mandatory relations, constraints, and relationships. Moving forward, and going more into depth into MLDCAT-AP and the DCAT-AP system, you might already know DCAT-AP. This is the application profile that is used, for example, in the open data portal of the European Union. And the main goal of DCAT-AP is to support the discovery and access to open data in a cross-border and cross-domain environment. How is this done? Well, by describing metadata that can be harvested across a distributed network of portals. In the form of the objectives of DCAT-AP are also expressed in the form of an application profile of the W3C standard DCAT. As I have also learned, DCAT was actually also started in the ISA action, and then it became a W3C standard. In DCAT-AP, we express constraints and usages of DCAT properties and classes, and then we also include additional properties and usages of controlled vocabularies. As domain of applications for DCAT-AP, we have, as I've said already, open data portals. We have base registries, metadata description. We use DCAT-AP. DCAT-AP is also used in data spaces. And now today we are going to be talking more in depth about the extension of DCAT-AP for machine learning. So explaining more about the DCAT-AP ecosystem, we have the W3C data catalog vocabulary for facilitating interoperability between datasets. DCAT is now at version 3, and this version extends DCAT 2 and introduces classes to support offline accessibility of datasets and datasets that are part of a series. And of course, the DCAT application profile, DCAT-AP, has been upgraded to the 3rd version, which is fully compatible and aligned with DCAT 3. And we have also DCAT-AP for high-value datasets, which facilitates the adherence to the high-value dataset implementing regulation with little additional effort. Here you have a picture of what is the relationship between DCAT-AP and DCAT, and of course the different extensions that exist for DCAT-AP that have been developed in SEMIC and by national administrations and other stakeholders. Moving forward, we can see that, of course, we have DCAT-AP that has been extended also at national level. And here it has been used to describe national data sets, or has been used in the context of national open data portals. And we have DCAT-AP DE from Germany, DCAT-AP from Italy, and DCAT-AP from other countries. And then we also have DCAT-AP domain extensions for describing domain-specific data sets. In SEMIC, for example, we have been developing stat DCAT-AP, health DCAT-AP, and now we are working also on the geo DCAT-AP new versions. We also can see that DCAT-AP has been used in the official European data portal. Here it provides access to data from all institutions, agencies, and bodies. And we know that the European Commission also uses DCAT-AP for its own data sets. In the European Open Data Portal, it aggregates data sets from DCAT-AP compliant portals across Europe. What are the benefits of DCAT-AP, using DCAT-AP and the associated ecosystems? Well, first of all, it enhances the findability and accessibility of the data. DCAT-AP comes with a decade of experience of documenting, maintaining metadata records, and sharing through harvesting. And it provides tooling to validate the implementation of the data. Additionally, it enables implementers to make data catalogs findable, so that makes it easy for them to have the data harvested. Then it enables implementers to express their metadata in a standardized way. And finally, it provides a collaborative environment that allows implementers to express their needs and additional requirements. So we have seen that DCAT-AP has proven to be very flexible, and it has been extended for different application scenarios and application profiles. So, but at the same time, maintaining the interoperability of these different models, because their core is exactly the same. Moving forward, we are coming to the focus of today's webinar on the MLDCAT-AP. How did we come to let's say this challenge, and how come we thought about developing this extension of DCAT-AP for machine learning models? Well, we have seen that the lack of semantic interoperability forbids the assets, including machine learning models, to be easily exchanged between platforms. And of course, now also in the era, we are now officially in the era of AI, and there are more and more platforms where AI models become available. But at the same time, we're also in the era of the AI Act, for example. So we need to make sure that when we do want to find a model, and when we do want to employ a machine learning model, we not only find the model based on the on what the model does, but we are sure of what the characteristics of the models are, of the data that it has been trained on. We can have access to validation and many other things that are important to have described when we are dealing with machine learning models. So given this challenge in the context of machine learning models, we have decided to define a common data model and enrich the existing API with semantics. The model that we have, the application profile that we have defined, MLDCAT-AP, is compatible with DCAT-AP 3.0. And of course, because it is tailored for machine learning data sets, it yields all the advantages of both of using the DCAT-AP, but also the flexibility to add all the metadata fields that are required in order to have the specific characteristics of machine learning models taken into account. By doing this, we have domain-specific benefits, which are the improved reproducibility, the integration of RAI principles such as transparency and then accountability. And of course, because now we have to be thinking about the AI Act implementation, by having the flexibility to introduce new metadata fields, we facilitate the adherence to the AI Act. We move forward. We see that, okay, artificial intelligence is the big field, and the big part of artificial intelligence is about machine learning, about model building and evaluation. So having an application profile that is able to describe machine learning models and everything that they comprise from the data which has been used for training, and that of course involves the collection, the preparation, and the accuracy of the data which is being used for training. Also the learning algorithm that is being used for the training, the data that is used for evaluating the model, and of course the methodology used for the evaluation, and of course the final quality of the model, which is given by the predictions and the evaluations of these predictions against a standard data set. So in a machine learning model, to describe it, it's much more complex than just describing a simple data set or a data collection. If we move forward, it is my pleasure to introduce our OpenML speaker, who will talk about the OpenML pilot and how we have come to develop this new application profile, which is specifically tailored for the machine learning domain. Thank you. And Peter, please, the floor is yours.
Hi, my name is Peter Gijsbers, and I'm a research engineer at Eindhoven University of Technology. And I'm also one of the core contributors to OpenML, which is why I was involved with this pilot program. So I will briefly introduce OpenML and the different concepts it has, and then I will share my experience being participant of this pilot program and why we decided to join this effort. So OpenML is a platform that wants to democratize machine learning, and we want to do this by making machine learning research easily accessible and reusable by giving frictionless access to all machine learning experiment data. So there's a bit to unpack here. We want to make sure that everything is easily accessible. So we want to have some kind of standardized way to access data sets, but also other parts of machine learning experiment data. So besides our data, we also want to describe the models that we may use in our machine learning experiments. And we want, of course, to also describe the results of those models that are being trained on the data. And we want to make sure that people can easily access all of this data and that they can also reproduce some of the experiments. For example, being able to reproduce the experimental setup easily. So to do this, we define a couple of different concepts in OpenML. And the first is, of course, the data sets themselves. On OpenML, you will largely find tabular data sets that are somewhat smallish. The larger data sets are still on the gigabyte scale for us currently. And these are tabular data, so you have just a number of rows and columns. You have text features, numeric features. They're all aimed at, for machine learning research. So they all pose some kind of machine learning problem, something that you may want to predict. Additionally, we also are working on support for deep learning data, so image data sets, audio data sets, etc. But this is in development and hopefully will mature over the next year. And here you see some examples of the datasets on OpenML. So of course they have the name and their description, but they also have other meta features that describe the datasets themselves that I will talk about a little bit later. When we have a dataset and we want to evaluate a machine learning model on it, we need to define a specific evaluation procedure. And we call this basically a task. So the task defines the evaluation procedure, for example, holdout, or as you can see here, a 5 times 2-fold cross-validation or a 10-fold cross-validation on the credit G dataset. Right? So there are different schemes to do this, but even for a specific scheme like holdout, of course, the split also matters. So we store information about the splits that are being used in experiments. We have information on which targets we want to predict, right? Which column in the data, and also which metric we're trying to optimize towards. This is not important for every single machine learning algorithm, but for some of us it really matters because they take it into account when building the model. And finally, of course, we also have the algorithms themselves, and we call these flows. They are basically algorithm descriptions. So they have a high-level description and a name, also some information about the different dependencies that you use. These are the software dependencies. But they also have often hyperparameters. For example, for a support vector machine, you have hyperparameters of C and gamma, or the kernel that you use. And these, of course, also affect the way that the model is trained. And these flows, they can be either entire descriptions of how to take a data set and build a model on it, or they can be parts of this pipeline. So for example, a pre-processing step, feature normalization, something like that, or just a classification algorithm. And these flows can also be composed together. So you can have a whole pipeline and all the different steps are described with their different hyperparameters. And then finally, when you evaluate such a flow on a specific task, then you get a run or the experimental results. So on OpenML, we store the predictions for such an experiment, and in some cases also the model itself. Though sometimes for technical reasons this is hard to do. And then OpenML will calculate various metrics on those predictions to assess the quality of the model. So all of these different concepts, all of this different data, you can browse through the web interface at openml.org. This is a great way to just explore the kind of data that we have. But if you really want to use this, for example, for your experiments, or you want to access this systematically, we also have a few other ways to access this data. The most generic one is the REST API endpoint. This allows you to basically fetch all the data that we have, but you can also filter through the data, search for the data here, and you can also upload new assets yourself. But of course, it can be a little bit cumbersome to always interface directly with the REST API. So in some of the more commonly used programming languages, we also have modules and packages which support access to OpenML programmatically. And this is how most people end up using OpenML, for example, when they're doing an experimentation for their research. So why did we decide to join this pilot program? Well, I just gave you a brief introduction of OpenML, and anyone that wants to start using OpenML basically needs to also go through this, right? So there's a bit of a learning curve. You have to understand what the different concepts are. And of course, if there's already a standardized language, a standardized specification out there that can describe all of these different assets, then someone already familiar with that doesn't really have a learning curve, or has a small learning curve to figure out, okay, what is specific to OpenML still? But for the most part, they understand these concepts and they know where to find this information. Of course, also programmatically, it's possible for other people to then interface with OpenML. With DCAT-AP already, of course, you have data search portals, but with MLDCAT-AP, this could be more generally extended for different machine learning applications. And of course, this would also work the other way around. When we sufficiently integrate MLDCAT-AP with OpenML, and we can define experiments on tasks that are described according to an MLDCAT-AP specification, for example, then we could even report on results for experiments which are done on datasets or tasks which are not hosted on OpenML itself. And this is very beneficial, for example, when we want to work with datasets which OpenML is not equipped to host, or maybe for technical reasons, or maybe, for example, because there are sensitive data in there. So how did the actual pilot process go for us? Well, we first had some discussions with SEMIC. We gave them this introduction to OpenML, and we talked about, how do you use this, and what is important for us. And we gave them some documentation on our existing schema, if you will, and we also gave them some examples and showed them how to get more examples from the APIs. And with that, they went to work and they started making a mapping. They mapped the OpenML schema to not only DCAT-AP, seeing where things fit in, but they also, in the process, were comparing to other platforms and standards, for example, Hugging Face, to see, okay, what also generalizes? What are the things we want to capture in something in MLDCAT-AP? And what is maybe perhaps more specific to OpenML? And we have some OpenML specific identifiers for that. So the end result is a schema. And the schema maps most of OpenML to DCAT-AP, or at least the datasets parts of it. So a lot of this already, of course, existed, but some of the things weren't supported. So sometimes we just have new properties for existing classes, and sometimes we're defining new classes altogether. And one of those things is the quality measurement. So a quality measurement describes the data values. And in the literature, you might also find this as a meta features. And these are simple ways to describe aspects of the data. For example, you have simple measures which have, for example, the number of rows, the number of classes, or the number of nominal features. And here already you see the first example of a description of a data set, namely the number of classes. That's more specific to machine learning, because in this you also have an understanding about, what is it that you want to predict in this data set, what is the actual machine learning task. You have also other sets of meta features or qualities, such as statistical ones, which compute measurements on the numeric data features in your data. For example, you can take the mean of means, or you can compute something about the skewness, and these also in some way express some characteristics of the data. You have information theoretic meta features, which are computed on the nominal features. And these also are often in relation to the target value of the class. So these are also more machine learning specific. And you even have landmarking features. These are features that are based on small models. So you train, for example, a small decision tree or a linear model on the data set, and you describe the model, the number of splits in the tree, the number of features used by the model, the performance of the models. And these are ways to characterize the data sets in which may be interesting also for machine learning applications. One way that this is used in the literature is for meta learning. So here we have these descriptions of the data sets, and we try to learn from those descriptions of the data sets and some experiment database. We try to learn the relationship between the characteristics of the data and the performance of specific machine learning algorithms. And this is just one example of how these qualities can be used. They're also very helpful when, for example, defining new machine learning benchmarks, because you want to, of course, filter through all of these different kind of properties. And for machine learning specifically, it's also nice to have, for example, these landmarking features, because you can look at, okay, is this data set very easy to predict, or do you need do you need to be careful with your model selection? Do some simple models work well and others not at all? Things like that. So it's very interesting. to work with for machine learning. And this is also why this is one of the more core concepts to MLDCAT-AP, as I'm sure will be elaborated later. And the end result is a number of different classes and attributes. So here you see how the different blocks relate to the different concepts in OpenML. The way that we went about implementing this was through Fast API. So we were already rewriting the REST API for OpenML from the PHP that we had to Python in Fast API for a number of different reasons. And we decided when we added these MLDCAT-AP endpoints for us, what made the most sense is still to work from the OpenML endpoints that we had and simply convert the data in the OpenML schema to the MLDCAT-AP schema. And for almost all cases, this worked very well. There were only a few small things where we needed to do some additional optimization or something slightly different to make sure that this gave a pleasant experience. And of course, in this process, SEMIC was also helping us. They evaluated the endpoints to make sure that we were adhering to the schema and helped us also understand what tools to use to validate the REST API that we were developing. And yeah, in general, they were very helpful also when we had questions about the schema and about the implementation. So this was, I think, an iterative process, but a rather smooth one and with very good support from SEMIC here. So the end result is a number of REST API endpoints that support at least the set of the dataset classes for MLDCAT-AP. These are not entirely finished yet, but a demo version, like an impression, is already online. And we want to roll this out together with the new API that we're working on sometime later this year. And with that, I would like to return.
Thank you, Peter. Yeah. I take control on the slides and I keep sharing my screen.
Are there any questions in the meantime from the audience? If not at this moment, feel free to raise your hand at any point or use the chat function. We'll make sure to reply or to discuss any questions.
Okay. In the meantime, I continue. Indeed, to summarize the work, the pilot that we've done, it has been done is we start in November 2022 and we continue on that aspect. The input was indeed from the OpenML API and the website on one end. On the other end, we put in place, let's say, we looked at what Hugging Face and on NX, also on NX, because there are some metadata to describe a machine learning model at that time, together with the DCAT-AP. So indeed, as already Peter mentioned, there was a big mapping exercise at the beginning, and starting, for example, directly from the property and the description of the dataset, which are indeed coming from the DCAT-AP. And that mapping indeed brought to the, let's say, to the creation of the first data model, which I call MLDCAT-AP 1.0 over there. That is indeed the main outcome of the pilot. We have done at the same time also a mapping with the schema.org from the DCAT-AP perspective, which contributed back basically to DCAT schema.org mapping. Because as already Alexandra mentioned, DCAT-AP depends on DCAT itself. And at that time, DCAT was preparing the mapping with the schema.org. So in reality, we contribute back, our finding will contribute back to the DCAT action. Going next, let's have a look, give a closer look to 1.0, and then we will move to 2.0. Because the 1.0 basically is the outcome indeed of the pilot with the OpenML itself. So it's indeed it's a model. It's comprehensive of different classes, as already Peter mentioned, and those that are on the top, highlighted in red, are concerned the DCAT-AP classes. I will look at them later on together, and next to it you have the one main creator class, which is the machine learning model class. I will look also in this in details. Starting from the DCAT-AP concept, we start to look explicitly what is on the properties of dataset and or distribution, because in DCAT-AP, dataset and distribution, they go next to each other. A distribution is indeed the concrete file or let's say data itself that it can be retrieved, so it can be even retrieved by an API, and that's why you have the concept of data service. OpenML describes let's say their dataset not only through the portal, so which itself is a catalog itself, but also through the API, described as an OpenML API, as Peter already mentioned. On the right-hand side, you see an example of OpenML dataset. Here it's the credit G, which has its own identifier. It has its own format, this R format. There are some keywords, for example, used to describe the dataset and its own description. And even, importantly, let's say a download URL. So these are properties itself, it's metadata that is described through the dataset and the distribution, let's say, classes and the data model. For the machine learning model class that I mentioned before, the initial thought is to look what exists out of there. First of all, by looking, for example, at Hugging Face and on NX. An example here we brought from Hugging Face. We have for machine learning model, you have a name, but also you have a description of it with some tags as well. So some evaluation results and etc. You have also into the card, what is called card in Hugging Face. It's in templating. You have also description of, for example, the intended use of let's say the machine learning model, and also the ethical considerations. Going forward is indeed the result, let's say, of the pilot was at 1.0. We continue the work on opening, let's say, on looking forward and see what can be done more out of after this pilot. And so that's the idea to create the version 2.0, because there we extended the model by adding by doing a comparative analysis between the different repositories of machine learning model, not only Hugging Face, looking also at how papers are usually introduced or related to machine learning models. Most of the time you see that either let's say a machine learning model is described in a research paper as outcome of some research. So the inclusion of algorithm is also important, as I was already mentioned before by Alexandra, and especially together with what we said before with Peter, the focus on data quality and also risk. It's important in view of the AI Office and AI Act. Then the entire model MLDCAT-AP 2.0 has been published in ReSpec in HTML format, so it can be publicly consulted, and let's say so people can even participate through GitHub into the, let's say, to the life cycle of data model itself. Indeed, as you can see on the right, the last version 2.0 is published already on 14th of February. Yeah, you can scroll all of it and see all the properties for the data model itself. Talking about the comparative analysis, as I mentioned before, we took in account 4 types of repositories, going back with Hugging Face on one end, Kaggle with that absorbed machine learning models from TensorFlow at the same time, PyTorch, and Azure AI. So what you see here in this table, some common properties for a machine learning model that have been integrated into the MLDCAT-AP. And I give an example here. One end, you have the language, when a machine model knows how to interpret certain languages. Reference to paper and code, that's also quite common, because indeed, when you have a description, as I said, of a machine model, most of the time, the publisher or the creator gives a reference to the paper in which the machine model has been published, let's say, together with. Other type of properties, like how to use the machine model with certain API. Sometimes these are can be integrated, for example, in Hugging Face API or in OpenML API. And a logo that sometimes allow you to describe certain actions. Especially this happens, for example, for machine model that use in for images. You have also files related or some let's say engagement from end user, like likes and downloads that can be used for in a catalog. A relation between machine learning model, which is important as well, because a machine model can be fine-tuned from another one, or is a variation of another machine learning model. That's it appears more and more in the description of machine learning models on the repositories. And then the creation date on the checksum, which is important also as well, because especially when the machine models are quite big, checksums are used, let's say, to evaluate if the file or the model file is still integer. So this comes indeed, the output of this comparison is indeed the enrichment of the class machine learning model that you see on the right hand side with different properties, including also then certain classes that you see on the left, like the bibliographic reference that it concerns basically towards the paper, an image object for the logo, and let's say an explicit creation of class risk, because that is quite important afterward for the, let's say, the AI Act, and the engagement, as I was mentioning there on the left, so with download and likes. So these are indeed, let's say, these are new classes adding that, but then you see on the right hand side also some relation like fine-tune from and as variation. So to another model. So the relation between another model can happen, as we've seen already in Hugging Face, but also in Kaggle as a type of expression. The part of algorithm is also important. It's important. It was already described, indeed introduced by Peter before, but it's important also because this comes out from the AI Office and the AI Act. The AI Office is working indeed with the different DG, especially with the European Center for Algorithm Transparency, to evaluate AI models. On the other hand, there is already an introduction of the AI Act of type of algorithms, and you see some examples here, extract from the AI techniques. Here it's defined. So you like, for example, supervised, unsupervised, or reinforcement learning, plus other type of approaches like Bayesian estimation, or even type of inference detecting engine. You can see this type of algorithms itself have been indeed considered, and when indeed the MLDCAT-AP 2.0 was indeed in preparation, we found out that there was already an ontology on machine learning and MLSO, machine learning cellular ontology, on which indeed the run of machine learning execution realizes an algorithm, and you see highlighted on the left. This algorithm can be of, let's say, there are two classifications from this ontology, and I welcome indeed Anastasia, which I see online with Ioannis. Thank you for joining the meeting. And indeed, we have two types of classification here: algorithm concept and the learning method concept. You see, those lists are quite comprehensive, and some of them, indeed, let's say, in those you see in bold what are already mentioned by the Act. So on the left-hand side, you see highlighted in Bayesian or deep learning algorithm or reinforcement learning algorithm on the left. And the learning method, we have still Bayesian learning, reinforcement learning, supervised learning, and supervised learning. So these basically allowed us to include the algorithm class from the MLSO ontology into the model. So that is included on the right there, you see. And there are two, indeed, classification included that are algorithm type and learning method type. And then another point of this model is the quality. As already Peter introduced, quality is quite important. We talk about quality of, in this case, of dataset. OpenML introduced a lot of quality measures, let's say 107, even more, I think, if I remember well now. This quality is also important. We've seen this is important also for other type of websites like Hugging Face or Kaggle. Most of the time when we have tabular format, you see that some statistics that are associated with the columnar basis, including, for example, as you can see in from Hugging Face category, it has 8 values for that column. Or you see also distribution of values in Kaggle itself. So quality is important to describe your data, the data set, and it's important indeed to measure such quality itself to see if it has because it has an impact on machine learning models. And this has been also included also, even though let's say not extensively, but from the AI Act, where high-risk AI system they should take into account indeed the requirement from high quality data, aside documentation, etc., traceability. But high quality data is important, and that's why the inclusion of indeed data, let's say data quality. You see on the right hand side the part of the model that is being impacted after all. So you have a quality measurement itself that comes from data quality vocabulary now, from MLDCAT-AP 2.0, and includes indeed the data qualities, which have been already described from OpenML. So a data quality, at least those 107 could be included in that part. Another part of the model, interesting indeed, the paper. I already mentioned about the bibliographic reference, but the bibliographic reference itself is a link that brings you to a paper. Research papers are important because indeed over there is the results of such analysis can brings to a data model, but sometimes also to a machine learning model. But sometimes over there are links with other data sets. While working on the MLDCAT-AP 2.0, we looked out of there what are kind of existing resources concerning paper, and we found linked paper with code. We have been in touch with the people, let's say, responsible for the linked paper with code, because this website allow already to express in the form on linked data different type of let's say concept. Especially paper. You see, paper is highlighted in the middle, but paper is not isolated, as you can see. It's connected with dataset over there. It's connected with a model on the right, and it's also connected with the repository. The concept of repository is important too, because in machine learning model are also hosted in certain repository together with also sometimes with the dataset itself. So in linked paper with code, the concept of paper was indeed important, and it's been integrated in the MLDCAT-AP 2.0. You see on the right and there, and brought by the bibliographic reference. So in a paper, you can have indeed an abstract to describe it, the date in which it has been published, the document, some document associated, the subject of the paper, and the title. And this paper indeed is linked to a repository in which, for example, a machine learning model has been hosted, or let's say simply published. I go to the Next slide. In MLDCAT-AP already in MLDCAT-AP 1.0, we needed to use different control vocabularies. This is to describe some parts that were coming from a dataset and distribution. And you can see over here in this slide 3 types of control vocabulary that we've been using. One is for access rights for datasets from publication office. The publication office already provides such type of list. The distribution format, so indicating that all the file types for a distribution itself, but also the language of a distribution. So in this sense, indeed, the publication office already provides certain certain control vocabulary that were already used. But already in 1.0, we need to add other new created control vocabulary, so 9 more, including, for example, dataset status, like if the status is active, deactivated, or in preparation, or the dataset visibility, if it's public or private. In case, for example, looking in the case of OpenML, you don't want to disclose the dataset, let's say, soon. You want to, it's at the beginning private, and then you make it private afterward, let's say public afterward, in order to be shared with the rest of the audience. So we had to add this new control vocabulary. Indeed, the control vocabulary are important, so then they need to be used also in MLDCAT-AP 2.0, including also new type of control vocabulary. We've seen already the algorithm side, because algorithm in the model has algorithm type and the learning method type currently taken from MLCO ontology, but also we have the machine learning model type as a way to classify machine learning models. And that is indeed important to find a machine learning model in a catalog, for example, when you want to describe it in an easy way, when you want to find it in a certain way. So definitely, again, some certain control vocabulary can be already used by a publication office. Others could be discussed, could be needs to be created, but also could be discussed on view of this data model. Now, it's time for questions. I hope, let's say, first of all, the presentation is clear. Well, we brought here in this webinar different people on board, not only OpenML, so we invite you here to give you the possibility to express your questions, because the idea is, okay, we want to move, let's say, we've done a pilot, but we want to move this and make it public with the rest of the community. So it's an opportunity to steer the data model, let's say the MLDCAT-AP, and to see where we, let's say, as a community, we could bring forward a new advice. Thank you in case for listening.
Are there any questions on the content presented? Maybe a question towards you, if there's no immediate questions. Do you see any relationship to your work? So I think we have a lot of people in the call that are active in this field. With what you saw today, do you see the relevance of the model, or do you have any thoughts on how it could relate to your work?
I see Michael.
Right, yeah. Hi, everyone. And yeah, thanks for the talk. Yeah, I've of course seen also my linked papers with code there and so on. Maybe, yeah, several questions. One of them is regarding, so we have these linked papers with code and so on. At the very beginning, we also talked about linked data initiatives such as Wikidata and so on. Is there let's say, a need or also some initiatives to go in, yeah, to check out what's possible there to interlink this, for example, because I see this could be interesting to link it to Wikidata or also to SEM OpenAlex and so on. This would be one question. And then the other question would be more what regarding future work, how you want to continue. Do you just want to roll it out, or are there any new ideas how to, yeah, for example, let's say populate this with actually instance data? Do you want to do this automatically? Maybe some ideas in this regard.
Well, I can reply for your first question. We didn't have let's say thought to look at the Wikidata or OpenAlex at this moment in time. Definitely, the fact that on one end we are connected with the datarope.eu, because datarope.eu, let's say, it acts as a registry of datasets. This could be, let's say, a possible link. Mm-hmm. But no, we didn't, let's say, thought about it. Maybe we could, let's say, if you have already any insights or some analysis that you've done, that could be already useful to start to look at it. Then your second question was on the next steps. But on one end, indeed, is to evaluate the model, because of course here there is not too much time to discuss entering all the details of the model. It's quite big. So there are, because of different relations or properties or even cardinalities expressed into the model, it's big to describe. That's for sure, it's the result of OpenML on one end, and we will try to keep the, let's say, the two model, the version 2.0, 1.0, possibly backward compatible, let's say, when but if it's we need to see how the model steers in one direction. There are some challenges, and I think in that way I can give the floor also to Anastasia, because there are some challenges. One is indeed the algorithm side, that control vocabulary are not easy even to agree on this, and so there are certain parts of the model for sure the community needs to agree. Please go ahead, Anastasia. And you are muted.
Okay, sorry. Can you hear me now?
Yes, yes.
Okay, I didn't want to interrupt the discussion, just wanted to put me in the queue. Very interesting work, first of all. Thank you for the presentation. I also have a lot of questions. The algorithmic side is definitely interesting. My questions come on, so you have the model, so you have described the model, and you have worked on a pilot with OpenML. What is not very clear to me is that how exactly OpenML uses the model right now. Is there an actual knowledge graph underneath, or is it just the model and the data are related to the model via the API? That was not very clear.
For the actual implementation, I leave to Peter to reply. I can tell you this. The REST API, it uses the let's say, express as a link data, and reuse the JSON-LD context that generated from MLDCAT-AP specification. But for the implementation, then I prefer to leave to Peter the floor. I don't know if Peter,
sorry.
Yeah.
Yes, so internally we still use the OpenML schema, as I alluded to before. So we just do the conversion at a late stage, basically. Yeah, and there, like Emidu already said, we just provide the linked data. So we have the different endpoints for the different concepts, and they kind of point to each other. I'm not sure if that answers the question.
Yeah, it does. It does. All right, thank you. And a second, let's say, burning question is about the quality aspect. Because I have worked in the past on a quality of data sets, And then if you look into that, what we know from literature about data quality, without considering models like vocabulary that can be applied to this data and produce RDF, is a completely different topic than having quality of knowledge graphs. Also because we have the open world assumption and the closed world assumption. So when we look into knowledge graphs and using annotations with vocabulary, then we think that the universe is all potential knowledge that we can have. But my main question is that if I understand correctly, if I understand well, so you use the data quality vocabulary, which allows you to create a different measurement. But then how exactly do you see this quality fitting to which are potential measurement that can be used? I would imagine, for instance, completeness of the data might be a typical measurement, which works like if you have a closed data set, because then you know, for instance, this is the table and this is all the data that I was supposed to have. But if you look into completeness in the case of knowledge graphs, then this is a little bit vague, because what is meant to be complete in that case, and how do you define completeness? Should all the information be in one endpoint or no? So that's the one thing. And the second thing that I always say about quality, look at the restaurants, right? So if I run a restaurant and I say I have good quality food, you can also say the same, right? But it comes with ratings from the users. And then you can have more information about the quality of a certain restaurant. So having a self-description of a quality, it's not always, it doesn't always reflect what the quality of a data set can be. But the quality of a data set depends on what the user wants to do with this data set. So I was wondering if there is, I mean, what is your take on this, and if there is any plan from OpenML to allow this kind of open quality given by the user for the data sets?
But definitely, it's not an easy subject in itself. Strive for quality, let's say, in all these type of measures that exist, and might not always be, let's say, clear. The same it happens on Interoperability itself. You see, over there, datasets are published and metadata quality is measured over there. The idea itself, it's not to say, this is the best dataset on the other one, is to try to, let's say at the end, show that if you put certain effort, at least to improve the quality itself, your dataset can be, it's easy to be reusable. No? The idea is to try to make your dataset valuable. So it's definitely it's a matter not to compare, but at least to try to measure over time to see, okay, it's something that some effort has been done to try to improve the quality of the dataset. Then for each single measure, of course, I think there will be discussion, of course, because then we need to see, make sense, certain quality measures or not. And also, here we talk about tabular data. Certain measures are interesting for tabular data. Maybe other type of datasets are not tabular, and then you can have other type of measures applied to such datasets. So it's something to be seen. I don't know if then Peter, you want to add on this?
Yeah. So indeed, some of the qualities or the meta features that I described don't relate really to quality, as you understand, of like how good is the data, right? They just describe the data in some way. But you can definitely have ones that, at least at some level, maybe can function as a proxy. So you can have things that automatically detect whether or not it's likely that there's, for example, label leakage in your data, which may be problematic if you want to then do evaluations and you're not aware of this, right? Or something like the suspicion for there being mislabeled data. Now, none of this is going to be like completely foolproof, but there might be some measurements which you can use here that can at least be a proxy. And then for OpenML itself, in terms of like, okay, what is good quality data? We also, on OpenML, we have the concept of benchmarking suites also. So these are the collection of tasks to standardize experiments. And the idea here is that people basically here do this filtering up and create a creation of data sets that they say, like, okay, these are good data sets that we should use for experiments. And we do also want to allow users to also contribute some of this to OpenML. But this isn't fleshed out completely. But I mean, also the automatically computed qualities that we discussed earlier, I think can be at least some level of proxy for this.
Okay, thank you. May I ask a last question?
Yeah, sure.
All
We
right.
have time. Yes.
Okay, my question is about shackle shapes. So far, I see that you have the model. A lot of like restrictions are defined in the model.
Correct.
And I was wondering, yeah, what is your position with shackle, and what is your vision, or how do you see things there?
But shackle itself, in SEMIC, we use shackle indeed to validate against the data model instance, let's say the metadata. And now there are in shackle in the shapes at least there are some restrictions on or checks, I would say, in that sense, on the ranges, especially on the cardinality. I think the one point of discussion of this model is for sure the cardinalities of the properties, because in some cases we could enlarge them. It started because again the model starts with from OpenML, and it means that enlarging them, it could be already a good possibility to be backward compatible, but restricting, of course, could be discouraged. And we need to see over time. We can see if indeed we would like to enlarge it. That also depends on simply feedback from the community. Say, well, actually, for my model, I need more than one property. Let's say the property repeated for that, so we could do it. And the same for the type of, let's say, or the type of classes, etc. So these shapes are currently automatically generated. In SEMIC, we have an approach that we design a data model, and in our own so-called toolchain, we basically generate automatically the HTML documentation and also JSON in the context and shackle shapes. So they are automatically, let's say, generated out of it. That helps for an editor like myself to just focus on the data model. So it means that enlarging already, or as I said, cardinality in the data model will be reflected automatically into the shackle shapes as soon as the new data model is published. That, yeah, let's say it's a way to for validate. And in that sense, in SEMIC, we already provide validation. For example, in DCAT-AP, there is already a DCAT-AP validator. And if there is a need, for example, as I see Florian put in a comment for use case, we could even create a validation service for MLDCAT-AP. That would be quite easy to do. Because then the validation service can already read automatically the shapes that we generate. So it will be synchronized automatically.
All right, thank you.
Welcome. I wonder if there are people. I see Miai from publication office. I hope let's say it's clear for the control vocabulary. Let's say, and when there will be some agreement, I think we'll come back to you.
Waiting for it. There is also a colleague I see from ISTAT. I don't want to point you out like this, Petri, but do you have any comments on MLDCAT-AP related to your work, or how it could be used in the work that you do at ISTAT in processing, handling statistical information?
Thank you very much for asking. We're still very incipient work, but we are very much looking into this. So I couldn't comment on it, but it's very interesting for us to have had this presentation and to know that you have this wonderful new standard. So yes, I mean, I couldn't comment from time being. Thanks for asking.
Thank you, Petri. Well, we'll always be, we can always be in touch in the future if you see more touch points, but good to hear.
Very much appreciated. Thank you.
Are there any other questions? Or Florian, I don't know if you wanted to ask a specific question that you put in chat.
Not in particular. I mean, I think we have gone through already some use cases that we have identified, and we have piloted with OpenML with Peter. No, I think it's more towards the audience whether they see those use cases valuable, whether they would be interested in trying it out or adopting MLDCAT-AP for such use cases, or whether they have new ones. And this webinar was more of an introduction. Of course, depending on the interest from the community, feel free to share this, and depending on this interest, we'll see what are also the next steps. So from that perspective, any inputs related to this is welcome, but it doesn't need to be right now.
Yeah, thank you, Florian. Okay, Emilio, shall we go to the final parts?
Yeah. Yeah, on the next steps, definitely the monitoring of the AI Act. We know that it's been approved from the Parliament, and it's a matter to be basically published definitely. So over there in the Act, we talk about AI, let's say, systems, which are software using models. So of course, the point of view would be definitely looking at the model side, which is covered part of the legislation. So we will monitor as soon as it is out to see what are the next steps for the model. See any type of feedback that we get, and of course, again, feel free to contribute on the GitHub repository. I think it's better to put on the link on GitHub repository over here, Nathan, on the chat. Because GitHub is used for all the SEMIC specifications and to gather input, and also to try to see if there are, let's say, implication between specification between all the specification in SEMIC. Sometimes, for example, DCAT-AP contributes back to DCAT because indeed certain questions are raised over there. And the same from MLDCAT-AP could be some certain question might be raised also to DCAT-AP. That's something of course to be seen. So feedback is really appreciated because it's important to steer even any feedback, even as I said, even changing the cardinalities for one property, or even discussing, let's say, the certain classes. For example, now the model is quite big. All the concepts, let's say, needed effectively. It's something that can be we can say yes, or simply to say, oh no, we could focus even on certain core of the concept. That's also something also to be subject to discussion. And of course, for us, it's important to continue building the community because it's a model is alive only thanks to the community, and not vice versa. So the community plays an important role into the evolution of the model itself. So anyhow, thank you. for being here, because then we can continue discussion on all this type of topic, from any single class to the control vocabulary that we mentioned before.
Thanks a lot for being here, everyone. I hope it was clear and interesting. You can always contact us for more questions or follow-up discussions, so feel free to do that. And if there's no further questions, then I think we can close the webinar here, and we see you another time.
Thank you very much.
Thank you, everyone.
Thank
Thank
you.
you.
Thank you. Bye.